Today we're going to talk about linear regression. I want you to think of regression as a cause and effect relationship. A cause and effect relationship. Okay? So when you hear the word regression, think of a cause and effect relationship. And when we do an experiment with a cause and effect relationship, we fix the cause and we observe the effect, because the cause causes the effect. So you fix the cause and then you see what effect it has. And the best way, again, to explain this is by using an example. Let's say the cause is ounces of beer drinking, imbibed, and the effect is the percent intoxicated. So we're going to do an experiment where we fix the cause, we fix how much beer is given, and we observe the effect, how intoxicated a person becomes. So what we're going to do is either give a person a fixed amount of beer or measure how much beer they actually drank, and then measure how intoxicated they became as a result. Now, it's clear that this is a cause and effect situation. I don't think anyone will doubt that if you drink enough beer, you won't become intoxicated, or if you happen to have been sitting there, you weren't intoxicated before, you now drank some beer, you got intoxicated, but it wasn't caused by the beer. No, I think it's pretty clear that this is a cause and effect relationship. So here's the experiment. 20 fraternity men are given various amounts of beer. Oh, we got permission from the parents and the university and the police force and everything else to do the experiment. Actually, it's not a real experiment. So the cause is the ounces of beer that was taken, and then they were given a drunk test. And that's the effect, the percent intoxicated. So we have a cause, we have an effect. We have a cause and effect. And what are we doing with that cause and effect? We're going to make a relationship between them. We're going to try and find out the relationship between the cause and the effect. And what we do is we've got some data, and we put the data on our graph paper, and most people would say, okay, what I'm going to do is I'm going to draw a line between the points. Let's see, that's a good one. Let's leave it there, and if I can't draw a decent line, not too good, but that's all right. Draw a line between the points, and that line would then represent the relationship between the cause and the effect. And if I wanted to know what'll 3 do, I run up here and I run it across there and say, oh, 3 does that much. That's how we will do linear regression. It's called linear regression. It's regression because it's cause and effect. It's called linear because I drew a straight line on it. If I drew a curved line, it would be curvilinear regression. But we're going to be interested in linear regression. We're going to draw a straight line through the data points. Now, how are we going to decide which line? Because there are many possible lines. Everybody can come and draw their own line and say that's the relationship. Well, what's the optimal relationship? And the way we're going to find the optimal relationship is to use what's known as least squares. Now, anyone can draw a line. When you do draw a line, you're not going to go through the points. The points are going to miss the line. Well, notice that the cause was fixed and the effect is what's variable. The effect is where the error is. And if this were the absolutely correct line, then the error would be the length of this line. This would be the error. And the error to this one is the error to this one is this big. The error here is this big. The error here is that big. And in order, the distance between the point and the line, straight up and down, would be the error in the y direction. So here I have some errors, and we're going to say the best fitting line is the one with the least squares. That is, take the errors, square them up. Someone comes with a different line, take his errors, square them up. Someone comes with a different line, take her errors, square them up. And the one with the smallest squared errors wins. That's the best fitting line. Okay? It's called least squares. The least squares fit to the regression. Now, there are 2 properties that are very important in linear regression. When you draw this line, we fit the line. I'll show you how to fit it in a moment, but once you fit the line, there are 2 properties which are going to be very important. In fact, these 2 properties will determine the line. And one of them is called the intercept. I like calling the intercept the residual effect. Residual effect. Because if I don't have any cause, zero cause. Still, I'm going to have some effect. The y does not go through zero. It goes through something above it. So if I extend this line to the y-axis and see where it crosses it, where it crosses the y-axis, that is when x is 0, I call that A, the residual effect, or the intercept. Where the line intercepts the y-axis is the intercept. So, okay? A is the intercept, or the residual effect. By the way, I should point out that some people call these errors residuals. And so don't confuse residual effect with residuals. I don't use residuals. I won't be using residuals, but you may hear it in the literature. Residual is the difference between the point and the line. That's the residual. The residual effect, however, is the slope, is the intercept, A. The slope, let's get to it. The slope is the rate of change of the effect with cause. If I make 1 unit change in cause, how many units change in effect are there? Now I'll make another 1 unit change in cause. How many? Same number. Look at that. The effect changes by the same amount for a 1 unit cause change. This is the rate B, the rate of change of effect due to cause. That's called the slope. It's actually the tangent of the line that this line makes with the x-axis, but we won't worry about that. The slope is the rate of change. And those two, if you give me the intercept and you give me the angle, I can draw the line. So A and B determined what the line is. And the way statistics draws a line is it finds A and B and then lets you draw the line with A and B. Okay? Now, how does it find A and B? It uses a formula. Of course, you know, formulas are only really good in homework exercises. You will not have to remember this formula past your homework, but you will have to use it in your homework. So let's use the variable x for the cause and y for the effect. We always put the cause, by the way, and you know, on the x-axis, which is the bottom, and the effect on the y-axis, which is the side. So it's sensible to label this effect y and cause x. Now, B, the way you get B is you take, well, we're going to have a column of x's. Take from each x, subtract off its average. X bar is the average of the x's. From each y, subtract off its average. Now, multiply together the corresponding x's and y's. That is, x minus its average and y minus its average. Every point in your graph has an x-coordinate and a y-coordinate associated with it. That's what graphs are. I mean, let's go back here. What is a point in a graph paper? You have an x point and a y point, and someone draws the asterisk there. Another point, x point, and y point. People draw an asterisk. Each point in the graph has an x and a y coordinate. And what I'm saying is rescale your x and y coordinates so that they're subtracting the average from them. So x subtract its average, y subtract its average. They're still associated with each other. Now multiply those things together. Okay? Now, add them up for all the points you have. That's the numerator. The denominator is take each x minus its average and square all those numbers and add them up. And we make a ratio of those two, and that's B. That's the slope. Now, A is easy. Just the average of the y's minus B times the average of the x's gives you the intercept. So we have the slope. Use it to get the intercept. This is the residual effect. This is the rate of change. This is a relationship, and the relationship, the linear relationship, if those of you remember your geometry, trigonometry, most of us don't, but if you do, you know that this is the relation, the straight line relation, and y, which is the effect, can be obtained by knowing A and B and whatever cause you're using by this equation. All you have to do is plug in the A you got, plug in the B you got, multiply by x, and you'll know what the effect is going to be. So we can actually predict an effect from a cause without any trouble if we know A and B. Just plug x in, multiply by b, add a, and that's going to be the resulting effect. Now, what's going on is that what you have are these points all over the place, and you draw a line between them. These points we know are in error. They don't hit the relationship. We feel that this is the best relationship. even though the points, perhaps none of the points, are on that line, that's the expectation. That's the expected relationship. That's what it should have been. But it wasn't. It was off. Well, we don't really expect, in the everyday sense, to obtain our expectation. So the expectation sort of in the center of all the data. And this line is really the center of regression data. That's the average, so to speak, of regression data, the mean of regression. It's actually the mean of the regression data. Okay? Now here's our example. Here's the first bunch of people we gave beer to. 3 ounces, 5 ounces, 8 ounces, 10, 13, 15. We're going up and up, and then we gave them the drunk test, and here's how intoxicated they were. That's the first bunch. Here's the second half. We gave more and more and more, 50 ounces of beer. Boy, he really had it, but he was 87% intoxicated. 48 ounces of beer, 99%. These are the averages, X average, X bar, Y bar. What we'd go back is subtract this from every one of these things and get new numbers, but they're still associated. They're on the same line. X and Y are on the same line. You then cross-multiply them in order to help get B. At any rate, let's say we've done the arithmetic. Okay? We then plot the data. Here it is. Here's a plot of that beer experiment data. The cause is down here. Remember, the cause is on the bottom axis, and the effect is on the y-axis. So the ounces of beer, which is the cause, is put here. The percent intoxicated, which is the effect, is put there. And we're going to draw a straight line through it using the equations that we have. And the straight line, who knows, it'll come out something like that, I guess. But let's do the calculations. Here are the calculations. For that data, I calculated x minus x bar times y minus y bar, summed them up, and I calculated x minus x bar squared, summed up, and I made a ratio, and I get 1.97, essentially 2. Rate of change is 2. That means you go up 2% intoxicating for every ounce of beer you drink. 2% intoxication for every ounce of beer. The intercept was minus 1.25. That's probably a little funny, but what it means is that if you don't drink any beer, you could expect it to be less than 0 intoxicated. Well, that just shows you that the line we get is not perfect. We're estimating the line. There's a true relationship somewhere. It probably goes through 0. Our estimate of the line looked a little like that. Well, okay, we can't expect to hit it on the button, but we hope to be close. The final relationship that we propose from the data is that y equals a plus bx, or that if you want to know how intoxicated someone's going to get, what you do is you say 2 times how many ounces of beer they drank and subtract 1.25 from that, and that will tell you how intoxicated, or what percent intoxicated they're going to be. Now, here's how we draw that thing slightly below 0, you see, slightly below 0, going up at a rate of, for every 10 units of beer drink, we go up 20 units. 20, you go up to 40. So for every 10 ounces of beer, there's another 20% intoxicated. For every ounce of beer, there's 2% intoxicated. And we draw the black line, and we can erase the original data. The original data really is meaningless to us. We only use the original data in order to find what we thought was the best relationship. As when we want to report something, we don't report all the data, we just report the average of the data. Well, in regression, we don't report all the data, we just report the line, the regression line, which is essentially the average of all our data. Okay, now what is regression? Regression is a cause and effect relationship. There actually has to be a cause and an effect. The cause is on the bottom axis, the effect is on the side axis, and we, by using our formulas, draw the best straight line through it. Now, we know it's not perfect, but it's the best we can do with the data. We draw a line through it, and that's a relationship. That's like the average. That takes the place. That's our estimate of the mean. It takes the place of the original data. And when we want to know what the effect is, we take the cause, run it up, and then run it across until we hit the effect axis, and we say, that's the effect I expect to get from this cause. Okay? Linear regression will be used for other things, so don't forget it. See ya.